This is A-level further maths, further pure 1 sample paper, question 7. This involves the second of the conic sections chapters. It describes two distinct points on an ellipse. They've given us the equation of the ellipse, so a good starting point is often to rewrite this in the standard format. So we can divide through by 4, get x squared over 4 plus y squared equals 1, and then perhaps even to write it as x over 2 in a bracket squared plus y over 1 in a bracket squared equals 1. So we can compare it to the more general version of a stretched circle, which is this. So we have a equals 2 and b equals 1. This suggests that if you start with a unit circle and you stretch it by scale factor 2 in the x direction, this is the ellipse that you end up with. So we could represent that something like this. We know that's roughly what it's going to look like. We also know quite a bit about its properties in terms of the symmetry, about the x-axis and the y-axis. And we also know where it crosses. So it might be worth jotting down these key ideas when you first encounter the question so that you can get a feel for what's going on. Also, sometimes it helps you to see what's happening with a question of this sort where they're describing tangents and various other results. Occasionally there's a nice geometric approach that will help here. Sometimes it's useful to use the parametric form or some other such thing. They're describing two distinct points on the ellipse, so they could be anywhere, and there's a line that passes through both points. The tangent to the ellipse at P and the tangent to the ellipse at Q intersect at a particular point. So the various lines we're interested in would be a line from a particular point to another point, so wherever those points happen to be, let's say there and there. We're interested in the equation of that line. We're also interested in the equation of the tangent at that point. And in addition to that tangent, we're interested in the tangent at the other point, which in this case is going to be a little steeper. Those tangents cross at a particular point, and that's the point with the coordinates that we're interested in for this question. So according to the question, the tangents intersect at the point RS. The line they're describing is the line L. So we're interested in that. I'm going to put capital L on the diagram so we can actually tell it's a letter rather than a number. This is the situation we're dealing with. So now we have a diagram, we have something we can work with and refer to and think about as we go along. Now this problem is an 8-mark problem, and that means you're left to fend for yourself a bit, to cast around looking for the right approach potentially. But what we know for a start is that we're interested in tangent lines. So it makes sense that we would want to find something involving the gradient. So let's start with that. We can begin with the more fundamental version, x squared add 4y squared equals 4, the original version they gave us, and we can differentiate implicitly. This is the easiest way to generate an expression involving the gradient without having to artificially introduce parametrics. So we'll get 8y dy by dx, and then on the right hand side is 0. So dy by dx is going to turn into minus 2x over 8y, or if you prefer, minus x over 4y. Now, we've just been told that P and Q are two distinct points on the ellipse. So it doesn't really matter where we put them. What matters is that we've got a couple of points and we're interested in their tangent lines. It makes sense, though, to give them some labels. So it might be that we decide P is the point with coordinates x1, y1, and Q is the point with coordinates x2, y2. Once we've got those in place, we can start to think about how our expression for the gradient is going to come in handy. Now bear in mind there'll be quite a bit of algebra in here. It's what's called an algebra heavy question, this kind of thing. But if we are careful and we keep track of what we've found and we compare it regularly to what we're trying to get to, we should find that that will help us to some extent. So we need the equation of the tangent at each of those points. So we'll start with the equation of the tangent at P. And because we've already found the gradient at any given point, that's going to be helpful for us. So the equation of the tangent at P, we'll be able to use the gradient function that we've computed. It's going to be minus x1 over 4y1. And then we can just apply the general formula, y minus y1 equals m brackets x minus x1. And in this case, the y1 and the x1 are exactly y1 and x1, because that's what we decided to call those points. We just need to fill in the value of m, which is minus x1 over 4y1. Now we can also get the equation at q, but because the only difference will be that we have x2 and y2, we should probably focus on writing this in its simplest form first, and then we can just write the analogous equation for q. So over here, we're going to try to simplify this. It's not clear how this is going to play out, but this is the general idea. We know two things about a line which is tangent to the ellipse. One is that it shares the same gradient. We've used that idea already. The other is that at the point that it touches, that point is on the ellipse. So in a sense, we've got the equation of the ellipse to fall back on. And if we can find somewhere within this equation, anywhere where the x-coordinate is squared, the y-coordinate is squared, multiplied by 4 and added on to the x-coordinate squared, we can replace it with 4, essentially. That's what we're hoping might happen so that we can find some connection and simplify this down to get some nice way of representing that tangent equation. So let's see what we get. Let's multiply both sides by 4y1 because that will get rid of the fraction for us straight away. So we get 4y1y minus 4y1 squared. And on the right hand side, I'm also going to expand out the brackets. So minus x1x plus x1 squared. Now if you look carefully, you'll see we've got the x1x term, we've got the y1y term, then we have a minus 4y1 squared and a plus x1 squared. Since x1 and y1 are the coordinates of a point which is on the ellipse, we know that they satisfy this formula. So we could either rearrange and use it directly, or we could say, since x1 squared is equal to 4 minus 4y1 squared, we could just substitute for that straight away. However you prefer to do it. It's possibly slightly more elegant to add 4y squared to both sides and simplify that way. But I want to show that we can do it this way as well. 4 minus 4y1 squared. And now things cancel out. So if you take a good look at each side, we find that the minus 4y1 squared appears on both sides, and we can just get rid of it. And then the other thing we might do is add the x1x term to both sides. And then take a look back at this. 4sy plus rx equals 4. We've got something very similar. In fact, I'm even going to put my x terms after the y terms so that we can see more clearly what's happening. Apparently, these two tangents intersect at the point RS. Where they cross is what matters. We're going to need to look at the other equation, the one from the point Q. But luckily, we've done all the hard work with the equation at P. So we can just write out the same thing, but with an x2 and a y2 in this one. But it's interesting that the equation we're trying to get to, that is supposed to be an equation for this line in terms of the coordinates of this point, that it should resemble so closely the equation of the tangents themselves. Now, the equation of the tangent that we've got here and the equation of the tangent we've got here, we need to solve simultaneously. we need to know where they cross. These tangents cross at RS, although it's not quite solving simultaneously. Because, of course, if we tried solving simultaneously, we get some answer involving x and y equals something using x1, y1, x2, y2. What we really want is to end up with a result in terms of r and s. So x equals r and y equals s satisfy both equations. That's the key thing that r and s have in common, that if x is r and y is s, then that point satisfies this equation, but also simultaneously this one. There are lots of points that satisfy this equation, any point that's on this first line. But if it also simultaneously satisfies this one, then it's on this line as well. And that's what makes r and s special. So let's substitute them in. We have 4y1 times s plus x1 times r equals 4. And similarly, 4y2 times s plus x2 times r also equals 4. Now at this point, we feel like we're very close because both of those look a lot like what we're trying to get to. Just to remind you, what we're aiming for is 4sy plus rx equals 4. That's what we're asked to prove. So, required to prove this. Now, we know something about r and s and x1 and y1 and x2 and y2. But think about what we're trying to get to. It's this line L between the points P and Q. So we could do with the equation of the line L. But when we generate the equation of the line L, it's going to involve x1, y1, x2, and y2. And that is where these two equations are going to come in handy. Because x1, y1, x2, and y2 appear here in the context of r and s. So there's going to be a bit more work to do, but let's see where this goes when we investigate the line between P and Q. So finding the equation of the line PQ in terms of x1, y1, x2, and y2. And let's see if we can construct this maybe without simplifying too far, just to see what it ends up giving us. Remember, we have y minus y1 equals m times x minus x1. And x1 and y1 can actually remain x1 and y1. But m is the gradient. And that's going to be the y step, so y2 minus y1 over the x step, x2 minus x1. This means we can rewrite our equation as y minus y1 equals this times x minus x1. Is that helpful? Well, there's a lot going on here. We want to try to get rid of y2, y1, x2, x1 from this equation because we want it in terms of r and s. Well, if we come back to these two equations, we've substituted r and s into these. What if we solve for r and s? If we try to find r and s, or in fact, even better, let's solve to find x1, x2, y1, y2, or some combination thereof in terms of r and s. In particular, we could do with knowing what y2 minus y1 over x2 minus x1 should be in terms of r and s. And that gives me a clue. If I take these equations and I combine them in the way that we might do if we were solving simultaneously. So I subtract equation 2 from equation 1. So equation 2 is the one on the right. In which case, the other way around. Equation 1 from equation 2. we'll have 4y2s plus x2r minus 4y1s plus x1r equals 0. The 4's cancel out on the right hand side. The other nice thing about this is that we can start pulling out common factors. 4s times y2 minus y1. This is now starting to look helpful. R times x2 minus x1. And that whole thing equals 0. Now we're very nearly there. What we need now is 4s times y2 minus y1 equals minus r times x2 minus x1. And if you remember, we're trying to get rid of this term up in this equation. So let's rewrite it so that we can see on one side y2 minus y1 over x2 minus x1 equals, it's going to be minus r over 4s. You might recognize back from the beginning when we first calculated this, minus x over 4y. It relates to the gradient of the ellipse at a particular x and y coordinate. Interestingly, the point RS is not on the ellipse, but the ratio between the x and y coordinates corresponds to the same gradient as this line, which suggests that there is a connection between the x and y coordinates that you would, if you were on the ellipse, the gradient of a point with the same proportion between the x and y coordinates. In other words, scaling this down, following a line to the origin, we should find that we get the same gradient there as we do here. In fact, there may well be a geometric argument to be made along those lines, thinking of a tangent line to the ellipse, which is parallel to L, and how the coordinates of R and S correspond to that. But we're not going to get into that now because we can get from here to where we're trying to get to. So we return to this line. Line PQ has equation this, y minus y1 equals minus r over 4s times x minus x1. We're very nearly there. We're trying to demonstrate that this line has the equation 4sy plus rx equals 4. We've got a bit more working out to do. So let's turn this into 4s minus 4s, multiplied by 4s, we get 4sy on the left hand side, minus 4sy1 equals minus rx plus rx1. We're not far off. Although we still have an annoying x1 and y1 that we haven't yet dealt with, we have most of what we need. 4sy plus rx can go on the left-hand side. And let's shunt everything else that we're not sure about yet onto the right-hand side. 4sy1 plus rx1. Remember what we're trying to get to is this. 4sy plus rx equals 4. And we have 4sy plus rx. So can we prove that this equals 4? Well, yes, we can. That was one of the equations we had. This one uses exclusively y1 and x1. And if we decided, for whatever reason, to use x2 and y2 over here, we could then just go back and use this equation. So now we can say 4sy1 plus rx1 equals 4. Therefore, 4sy plus rx equals something which is equal to 4. And that is the result they asked us to prove. Now, if you found that somewhat hard to follow, I don't blame you. I did as well. This took me a long time to get to the bottom of. And although, as is usually the case, the mark scheme makes it look like it should have been obvious, it doesn't necessarily feel obvious when you're working through it. The key things to spot were the algebraic way of making lots of things cancel out all at once. So we have a look at the beginning. They found the gradient. You get a mark for finding the gradient using implicit differentiation, which is good. And there's a second mark for finding the equation of a tangent at a particular point. There is a third mark for noticing that we can simplify that. So if you think about the kind of things you would do if you're trying this and struggling to complete it, you could at least find the gradient at a point, because that seems like an obvious thing to do if we're dealing with tangent lines. You could then use that to find the equation of the tangent at a particular point. And then a bit of messing around with this would have got you the third mark, demonstrating that because we have that 4y squared plus x bit, we can turn it into 4. You'll notice how they rearranged to get x1 squared plus 4y1 squared, which therefore must be 4, so you can swap it out straight away and get this. For the fourth mark, they say that because they intersect at RS, you can substitute R and S into both the equation involving x1 and y1 and the equivalent one involving x2 and y2. From there, you can go back and find the gradient of the line, y2 minus y1 over x2 minus x1. This skips some of the algebraic working out that happened in between. This was mostly this stuff we've got here, where we've got two equations involving x1, y1, x2, and y2, and r and s. And by rewriting sufficiently, we can get it in the form y2 minus y1 over x2 minus x1. And that allows you to then write the equation of L in this more simplified form. So for that seventh mark, it's getting down to here. And at the end, rewriting this in a form that we can tell is going to simplify down. And at each stage, keeping one eye on the result you're trying to prove and seeing what's similar and what's different will often be very helpful.